Hello, everyone. I'm going to talk a little bit about how we're kind of reinitializing the field in quantum chemistry using a hybrid architecture with Python and C++. So probably the first question that you have is actually, what is quantum chemistry? Which is probably a valid question. And so what I've done to explain this is I put biology on the left up here and physics on the right. And kind of quantum chemistry is everything in between, especially when it comes to modeling. So on the left, you have something called molecular mechanics, and they use it to model systems the size of like 300,000 atoms, because this is really like the size where life really starts to come about. The problem with this, though, is they actually completely neglect electrons in a system, and if I think about physics, I really need to pay attention to these electrons. And so if I go all the way on to the left over here, and I have physics, I worry a whole lot about my electrons. I actually solve the Schrodinger equation, which creates a wave function that kind of dictates how these electrons interact by each other, as determined by this little potential up top. However, the problem is when we do that, we can only do about 3 atoms or 10 electrons. So it's not really a useful system. And the reason that we can only do systems so small is simply because this fact that the scale is like n factorial. Because it's fundamentally an NP-hard problem, it cannot be expressed in polynomial time. So quantum chemistry in a lot of ways can be thought of as building approximations to this really highly accurate method which encompasses all the correct physics. So as we start making more and more approximations, we get scaling that's going to be, scaling that's going to be a little bit less. So in this case, n to the 7th. So n to the 7th is still extremely poor scaling, but it's really the first method in our arsenal that really can start capturing all the physics in reasonable amounts of time. And when we do this, there becomes many different ways to make these approximations. However, at the same time, we can start doing things the size of a DNA base pair. And so we can make more approximations, and when we make more approximations, there's more ways to actually make these approximations, so we get more and more methodologies, all the way down to when we start scaling like n to the 4th. So n to the 4th is actually the lowest scaling you can get away with in quantum chemistry, and what this means is that all the methodologies that we program have to be extremely efficient because the scaling is so steep. However, when we do drop down to n to the 4th, we can actually start modeling things like ligands inside of a protein pocket, as shown here, which is about 3,000 atoms. Still 2 orders of magnitude less than biology, which is really where we're heading, but we hope that biology and physics will eventually meet one day. So for us, the question becomes really, how do we actually manage and actually give some kind of program that can actually compute all these methods in a computationally efficient manner? And so right now, we do this through many different programming packages from developers all over the world. So I've shown about 15 up here. About half of them are free. About half of them will run you about $4,000 for an academic license or like $40,000 for a government license. And then if I really look into each one of these, the problem is that each one of these programs does something in the best way. So not only do they have every single methodology built in, each program is specific for one methodology that I really want to run in that given program, so I need to run all these programs together. In addition, these things started really about 20 years ago, and they become huge programs over all this time, encompassing about 1 to 5 million lines of code. So overall, simply gigantic, and all that code is written in Fortran 77 because that was simply the lingua franca of the time. There is a smattering of modern Fortran and C++ coming along, but for the most part, it's really a much older language. I want to show a little bit more about current input programs. So as it led on really nicely, most of these Fortran programs, they have some kind of input script as noted here. You have some kind of way of specifying the geometry up top, some kind of methodology for what you're actually going to run, and then some even more input that I'm still not even quite sure what it does because I just grabbed it off the internet for this one program. A coworker then came by and said, hey, that actually won't run. And I was like, oh, why not? And they're like, oh, it's missing a comment line at the top. And I was like, oh, that's not online either. So just kind of giving you an example of current input scripts. And I also want to read a nice little mailing listing that I ran across. Because the problem is there's only so many developers in quantum chemistry, and because they're distributed across such a large amount of codes, different pieces of the code get very well outdated. So in this particular case, it reads, that module mostly consists of code from a given program, which was written before the moon landing. Changing the code in the way you propose to accommodate larger molecules sounds good. And then in addition, my favorite thing about these things is they're written before like really Git or any kind of version control. And so you end up with about 30 files that contain 1.2 million lines of Fortran code in a single folder. So we kind of want to kind of update all these programs that have kind of aged a little bit. So how is Psi4 different? So first of all, we are a hybrid Python C++ program. We're also completely free and open source. And one of the things that I really like about Psi4 is we only run about 750,000 lines of code. And considering the number of methodologies or just numbers of acronyms that we support, we're really quite full-featured for those numbers of lines. And we really get away with this hybrid Python C++ architecture. We also have single node capabilities. Most of quantum chemistry is run on single node just because we do not parallelize between distributed all that well for most methodologies. However, we also have distributed and accelerator capabilities where applicable. All right. So let's actually start programming up a method in Psi4. And so what I've done here is I've shown self-consistent field. And what this is doesn't really matter, but it's really the base method for over 40 or 50 methods that all scale like n to the fourth. So this is actually one of our most workhorse methods in quantum chemistry. And so if I look at the very topmost equation, I see a bunch of things in black, and then I see things in blue. So everything in blue is actually quantum chemistry, where we have some kind of basis set, and integrals are expressed in this basis set to build tensors. However, everything else in black is just simple linear algebra. So for example, up here, I have a generalized eigenvalue problem, where C is going to be my eigenvectors, epsilon is going to be my eigenvalues, and S is going to be my overlap matrix that I need to diagonalize. Then to build this F matrix, it's just a sum of 3 more matrices. 2 are built from linear algebra, 1 is actually quantum chemistry specific. However, the 2 matrices I really want to focus on most are these J and K matrices. They're built by contracting a gigantic 4-index tensor with a 2-index tensor to build a new 2-index tensor. And so this is really going to be our rate limiting step in multiple ways. The first of all, 1,000 basis functions isn't unheard of, which is going to run you 8 terabytes of data for something that's fairly small in quantum chemistry standards. In addition, it's the only step in this methodology that scales like n to the fourth. All right, so to begin to program this up, I say import Psi4, because Psi4 means quantum chemistry, and I say import numpy as np, because that's linear algebra. Then what I can do is I can actually build a new molecule, and instead of using some kind of XYZ Cartesian input, what I can actually do is I can just grab it from the NIH database. So this is one of the first reasons, or first places where this Python really helps us out. Because writing this in Python was something like 35 lines of code. I can't even imagine trying to write something like this in C++ or Fortran. It would be a complete nightmare to do. Now, once I have my molecule, I need to build a wave function. Like I said, we're quantum chemists. We like to use wave functions. So I give it a molecule, and this next string is just going to be some kind of basis set specification. Once I have this, I can actually start building up tensors. And so if I want to make a matrix integral helper to make matrix integrals, I can just build it with one little line of code, all Fortran. And then I can start asking it to compute these tensors over and over again. And so what's really neat about this is this actually returns a Psi4 matrix, which is a matrix class very specific to Psi4, does many things that we're interested in. However, at its core, it's just a double star. And if it's a double star, I can write the array interface in NumPy and very easily export it out to NumPy. So once I have all these quantities, they're really quantum chemistry properties, in NumPy, I can just use NumPy as you'd expect, where I can either call NumPy's built-in vendor blast functionality, or I can call a nice little function by INSUM, which does this contraction for us. So in about 20 lines of code, you need about 10 more lines for the iterations. You can actually write yourself an SCF program. You know, C++ side, all told, this would run you about 10,000 lines to do something very similar. So we really want to focus on HPC here. And if I notice that I have Hadamard products, which can run me n squared, so I don't really care about those. Anything that runs me n cubed is actually going to be a blast call, so that's going to parallelize well on a single node. And so the only thing that really doesn't parallelize well are these J and K objects. Of course, quantum chemists have spent a lot of time thinking about these J and K objects because they really are the workhorse of quantum chemistry. And so therefore, there's many ways to do this. You can do them using exact integrals as shown. There's also sparse and rank-reduced techniques depending on what size you want to accomplish. In addition, you really have to think about the architecture that you're running on. So a shared memory versus a shared memory and disk is going to run you something completely different than like a massively distributed that uses accelerators. So all in all, you can actually come up with about 10 discrete, well-defined algorithms, and Psi4 is actually going to give you all these right out of the box. So the first thing we can do is we can actually just build ourselves a new JK object. This object is going to, unsurprisingly, compute J and K matrices for you, and you give it a basis, and then you actually just specify with this df which of these algorithms that you want. So in this case, df actually means shared memory ring reduced, so it'll actually parallelize really well on a single node. So I can just go ahead and pick this algorithm out of the box, and then I can initialize it. And because this is a Psi4 object, I need to give it a Psi4 matrix. So what I do is I build myself a new Psi4 matrix of size P and Q. And then the last little trick that I'll pull with NumPy is that because these things have the array interface, I can just simply append this array interface to these objects so I can access them just like NumPy. So in this case, I'm just setting this entire Psi4 matrix, which is a really nice expressible C++ class, using NumPy in a single line of code. So once I have this D matrix, I can actually give this D matrix to the object. It's a standard vector at its core, so pushback makes a lot of sense. And I can simply ask it to go ahead and compute these J and K matrices for me. So instead of relying on NumPy for this particular operation, I can rely on Psi4 instead, and it's going to actually parallelize extremely well on a single node. And if you're using the distributed algorithm, you can run about 100 to 200 nodes before Amdahl's law really starts to kill you. It should be noted that the distributed algorithm will actually go all the way up to something the size of the Tani supercomputer. It was recently benchmarked on there, and the 3,000 atom example that I gave initially was actually done using this algorithm. So you have an immense amount of power using Python side and very few lines of code. So we talked a lot. There's even more methodologies that can be expressed in kind of this hybrid architecture where you can write small pieces in C++ and call them in Python side. However, we have a lot of methodologies that are based on tensors. And these tensors can have anywhere from 2 to 10,000 terms in them, so they're actually quite expressive. And they're going to look something that looks like this. And so all this is, if you look really closely, is just a string of tensor manipulations. Most of the calls are going to be dgem, some of them are going to be AXB, et cetera, but it's all BLAST effectively. So if it's all BLAST or just linear algebra, I can actually go and start writing this out in NumPy and get myself a reference implementation. Or what's becoming more and more popular is actually going straight from like a LaTeX version or other versions of these equations and simply automatically build NumPy. So we can have a reference implementation in almost no time. And you can imagine that if I have 10,000 terms that I need to program up, reference implementation that I know is correct is something that is extremely useful to me. In addition, you can actually start looking at these things instead of using INSUM. You can actually reorder all the contractions and make sure they call the vendor BLAST or NumPy, and making sure the contraction order is the most optimal. And so you can actually do this automatically using Python as well. And if you do this, you can actually get a reasonable speed up. So on a single node, it can actually parallelize reasonably well. And if you're interested in this kind of thing, you can go to this project below. So the last thing I'll say about this is that there's no generally useful HPC tensor library out there yet. I know a lot of people are working on this, and we've tried a lot of them out. So if you want a really hard case for your tensor library, come talk to us. We'd really love to talk to you about these kinds of things. All right. So we talked a lot about programs which kind of assume that the developer knows how to develop everything. But due to funding considerations and the overall open source philosophy, a lot of developers are becoming narrow developers, as I call them, which means that they only develop a single methodology, but they do it really, really well. And this is the kind of people that we actually want to support the most, because they're going to write something much more efficiently than I am if I'm writing 12 methodologies, and they're only really focusing on one. So we really like these kinds of people, and it makes it extremely easy to interface to them with Python, because we can write interfaces at the Python layer when we link into them with the shared object, or what's becoming even more common these days is they're simply rewriting things with a Python interface. So we're becoming much more AstroPy-like. We really like this community, and we're hoping to follow this kind of model as we continue. And if we do this, we can actually use Anaconda to actually build up an app store. And so you don't actually want to download all these binaries and link to all these things at the same time. So what you can do is you can say conda install Psi4, and then if you want any other package, you just simply go to our conda channel and you say conda install other package. So in one line of code, it makes it extremely easy for our users to link into a very wide area of development. So really happy with content in Python in this particular way. So let's talk a little bit about non-developers. I guess we should really call them users. And so before we get into this too much, let's think about what a typical input file would be. Say I need to run 10,000 different molecules through some kind of given method. What I have to do is I had to write myself a script that would find the molecule that I wanted, write a new input script with this molecule, run that file, parse the output, and then finally put it into something that's machine readable, like CSV, HDF5, you name it. However, if I'm in Python and I think about large data sets, what I actually think of is I think about pandas. And so what we can actually do is we can just give some kind of file names, which is like a list of files containing molecules. I can loop over this list of files, read them into XYZ, and then I can just call energy SCF. All of our users never see the J and K builders and Fock matrices and linear algebra. They just want to say like a single acronym and get the result. So this is what most of our users use. We can then grab every single variable that SCF produces, and it produces between 30 and 40 variables using this grab globals. This returns a dictionary, which can be turned into a panda series. We can then concat all the panda series together, have ourselves a data frame, and instead of doing all this by hand with some kind of script, we can actually replace all of that with about 12 lines of Python code. So our users really love this kind of thing. And when we do this, we're just able to get about an order of magnitude more data than we ever have been able before, and it's really helping us in the quantum chemistry field to really look at data analytics. We recently had this paper that had these graphs in them. So they're neat graphs, but at the same time, the database size is about an order of magnitude larger than anything else in literature right now. So very happy with these kinds of techniques. And the last thing I want to say real quick is a little bit about interoperability. So there's all these packages out there that contain millions and millions of lines of code, and some of these things are extremely highly optimized, and we don't really want to leave these things behind. So in a lot of ways, Psi4, the C++ side, is just like any other package. Yeah, there's some clever things that we did with how we call it and the modularity of it, but overall it's just a package. And all the Python logic that we have in post-processing can actually be applied to any other program because it's universal. So one of our latest things, and very similar to the last speaker, is we're actually stripping out all this Python logic to think of it as like just a driver. So all the logic goes into a single driver that we call QCDB, and from this, we're actually able to call other programs. And if you want to learn more about this, Lori Burns is also a Psi4 developer. She'll be talking at 11:30 here on Friday a little bit more about kind of strategies involved with this. With that, I just want to say that Python has really helped accelerate development. Our users love it because the input syntax is so expressive. And just overall, it's a great way of doing things because it makes so many projects so much easier to do. And I just want to point out that the Psi4 is a gigantic collaboration between many teams throughout the world. And we have lots of funding agencies giving us money to actually do this. So hopefully this will really take off. We really like the open source aspect of this, and we couldn't do it without the funding agencies. All right, so thank you for your time. If you have any questions, I'd be happy to answer. Yes. Oh, so you're talking about chaining different methodologies together? Yeah, so if I got it right, the question was, how do we keep track of all the different methodologies, and especially with regard to chaining them together? Is that approximate? Mhm. So There's very few methodologies that actually chain off each other in quantum chemistry. So for example, I use the self-consistent field example as it provides a basis for higher level methodologies. But SCF is always used. I can't, there's no reason you can't use SCF, but it's just the de facto standard. So it's never really become a concern for us. As far as just the different approximations made, there's no real way to keep track of this, especially once you plunge down into the end of the fourth methods, because there's so many different strategies used. You have to actually just examine their papers and figure out what they actually did. It's actually one of the issues in quantum chemistry today, because there's so many approximations coming out that it's almost hard to keep track. Well, the implementations are static. Like, they will give you the same answer in every code. If you know it, yes. Yeah, that's absolutely one of the problems with us, and I actually hope that this kind of very high-level writing of methodologies will take off. I really hope to use this as kind of like a reference method where you can always look back at the hybrid NumPy code to actually see what someone's done. Because absolutely right, even in a paper, you don't actually have all the information that you need to reproduce that method.
So when you create a molecule or an atom, do you specify its
Absolutely.
track it?
I mean, it's with the output data. Yes, it doesn't change. Well, it does change in certain circumstances. I'd be happy to talk to you after we can get some more questions. Yes?
What kind of work are you doing for outreach to kind of make people aware that this is a thing in quantum chemistry?
The question was, what kind of outreach are we doing to really make Psi4 known? Two ways. First, we have a publication. We go to conferences. In addition, we have something called Psi4 Education, which actually teaches new people to the quantum chemistry field using this kind of setup. So instead of conventional, Fortran binaries.